Okay, good morning, everyone. Welcome to the ZEUS Town Hall that we've got prepared for you, where I'm going to talk about the facility progress and the first call for proposals. So I am Louise Willingale. I'm the Associate Director for ZEUS, and we've also got on the line Carl Kruszelnik, who's the Director for ZEUS, and a few other people from ZEUS who you may get introduced to in a moment. So today I wanted to go through the things I think are most relevant for our potential users of ZEUS. So we're going to start by looking at what ZEUS can do, what it's going to do for high field science and beyond, and how that you can think about how that might fit with your research. I'll then go through the different target areas where the experiments will be performed and the flavors of the science that we anticipate being performed in each of the areas, because they have each area has slightly different capabilities. We've got the expected 2023-2024 capabilities for each of the areas prepared. This is what we anticipate being able to offer in terms of the laser power, etc., in each of the areas. I'll then have a few slides on how users would access the ZEUS facility and what our proposal process is going to look like, which we're hoping will be announced this week. So there will also be an extensive question session at the end for anybody who wants to ask us questions as well. Just to begin, ZEUS is a facility, and this isn't just a machine. We've got lots of people involved in preparing and building the machine. This isn't everybody who's ever contributed, but it's some key people. So we have 5 faculty who are involved with the original proposal and are involved with overseeing ZEUS. We then have some more research faculty in various positions here who are involved with building the facility, and they're going to be involved with managing the facility and running the facility. So we have people who are more geared towards the experimental areas, people who are more geared towards the overseeing the laser, and people who are overseeing the engineering and involved with those aspects. For building the facility, Franco Bayer is our project manager who's overseen the whole project. And then we have, I'll come to these later, but each area is going to be overseen by what we're calling our link scientist. And the idea is to link the facility to the outside users. And so these will be very knowledgeable people who will help manage and build the connections for the users with the facility and oversee the experiments. We then have various laser scientists and engineers who will be running the laser, and the users will come in and work in the target areas, and so they'll be working very closely with the incoming users as well. We've recently taken on a data scientist. We're anticipating there being a lot of data from the experiments, and so we're building up a system to collect and store, and then have an access system for the users to be able to see their data after their experiments. We also have an on-site target fabrication specialist who will be helping us prepare targets. And a little bit outside, we've got an outreach coordinator, outreach and education coordinator who will be involved with telling people about the great science that we've been doing and those kinds of aspects. We also have a website. This is the old version. We're hoping to launch a brand new version. It'll just look a bit different tomorrow, so keep your eyes open for a new look website very soon. Oh, and I've got a team photo from a couple of weeks ago when it wasn't quite so cold outside, but these are most of the people who've been involved in the project. So ZEUS is actually an acronym. And so what does this acronym stand for? I apologize if you've seen me do this before. It actually stands for Zettawatt Equivalent Ultra Short Pulse Laser System. I think the ultra short pulse laser system bit is kind of clear, but where does the zettawatt equivalent come from? So as we increase the electric field strength, we are able to approach different conditions, and eventually we start to ionize material or reach the relativistic regime where we can accelerate an electron to its rest mass energy in a micrometer, the wavelength of the light we're using. The current laboratory record is a couple of orders of magnitude above this threshold, but there's a very interesting field strength where we can break down the vacuum and spontaneously create electron-positron pairs. This is at an enormous electric field strength. And if we wanted to reach this field strength with a laser pulse, we'd need to reach the critical field of 10 to the 18 volts per meter, which would require a zettawatt power pulse. So we only have 3 petawatts with up to 3 petawatts with ZEUS. So we are not going to be a zettawatt power facility, but we achieve this equivalence by playing a trick. We are going to have the ability to generate GV class electron beams and collide those with very high intensity laser pulses, so that the intensity experienced by that GV electron beam in its rest frame of reference will be equivalent to the zettawatt power pulse. So that's where our ZEUS acronym comes from. And we are well on our way to completing the construction of ZEUS. We started late 2019, we were funded and we started the construction project. The design phases took place. We started ordering parts, and the whole building was, in fact, nearly the whole building was renovated to make space for the ZEUS facility. Miraculously, considering COVID and all the other external factors, this was complete when we expected, and we have already started to launch operations into one of the target areas, and late 2023 is when we're due to start offering time to external users. This is all looking pretty good at this point. And so we're looking forward now to launching our operations and having users propose experiments to us so that we can start the preparation cycle to bring in external users. I'm not going to go into the gory details of the facility, the laser parts itself, but this is just an overview map of the facility. We have down here the laser clean room in this yellow area here. It starts with the front end over on this side, and then the various pumps come in and the pulse is amplified. It can go to one of two, well, it can go to both compressors at the same time. We have a 500 terawatt compressor or a 3 petawatt compressor. They have slightly different sized gratings, but this gives us the ability to do a number of different configurations for the different areas. So I'll start at the end. So with target area 3, this was actually an existing Hercules target area, and it has, I'll go through the different flavors of the research in a moment, but it can accept pulses from the 500 terawatt compressor. We then have target areas 1 and 2 over here, and these are newly constructed areas to perform experiments. We then have some other areas. We have an experimental control room where the users can sit to run their experiments, and we have some target preparation areas over here as well, and diagnostic preparation over here. So now what I'm going to do is run through each of the experimental areas and tell you about the different configurations we have and the sort of different flavors of science we anticipate happening in each area. Ooh, oh, I had some photos of the different areas. So in the center here, you can see the pump lasers and the amplifying chain on the left, and I believe that's a 3 petawatt compressor over here on the right. We have the front end installed and operational. Target area 3 has already performed its first user experiment. The users here are standing in the experimental control room. And then the target area 1, which is where the signature experiment of the colliding beam will take place. And target area 2, the preparations are well underway here. To begin with, we have a slightly smaller chamber than we will eventually have. So this is the old Hercules, what we call solid target chamber, that you can see being assembled down here in this target area 2. We have a few other spaces available to help offer the experiments to users, including an upgraded machine workshop, an electrical workshop, target fabrication and characterization suite, and offices for both the staff and the visitors to the facility, and some meeting spaces as well. So target area 1, I've kind of cut out this schematic here. So the laser is down on the bottom left, and we have various ways to get the light into the target area 1. We can take all of the energy available through the 3 petawatt compressor and send it down to a very long focal length parabolic mirror. So that we can focus it into the target chamber over here with a relatively loose focus. The idea is that this would be advantageous for laser wake field acceleration type experiments. We also have the ability to split the beam, so to take 2.5 petawatts to the 3 petawatt compressor, and then the other 0.5 petawatt to the 500 terawatt compressor, and take both of those pulses to this target area 1, so that we can send part of the beam to the long focal length and have a short focal length in a colliding geometry in the main chamber here as well. So we think of this as our signature experimental area, in that we can use the long focal length for laser wake field acceleration, generate the high energy, the GV class electron beams, and then collide them with the high intensity laser pulse to get the zettawatt equivalents. So the flavors of experiment that might be done in here would be laser wake field acceleration with the very high power beams. We could collide the electron beam that's generated with a high intensity laser pulse, and then there might be experiments that may like to use the electron beam to create very hard photons for perhaps looking at investigating nuclear materials. And at the bottom here, I've got a cartoon design for one of these signature experiments, which involves creating an electron beam from a gas target, studying the resulting electron beam using a semi-permanent high energy magnetic spectrometer that will be installed into this chamber. There may be additional focusing of the electron beam to the collision point for the signature experiment, and then there'll be significant local shielding that will be required around an electron positron and gamma spectrometer that's being designed as well. Next up, target area 2. So initially we're going to be initially we'll be constrained by the chamber size that we have in this area, but eventually we'll be able to upgrade to a 3 petawatt chamber as well. That should be happening over the next couple of years. Here we're anticipating installing a short focusing geometry and having a double plasma mirror setup. So in the photo over here, these chambers at the front in the foreground, these are actually to install the double plasma mirrors, and then the chamber behind is for the actual experiment to take place. And the flavors of experiment that we expect here, because the plasma mirrors give excellent contrast, we anticipate these being typically solid target experiments, so we can achieve very high contrast and have the solid targets without pre-plasma or ultra thin targets without pre-plasma in this area. And the short focusing configuration will give the smallest focal spots and therefore the highest intensities. Proton and ion beams or neutron sources, high harmonic generation, or schemes for gamma beam generation might like to look at this target area for their experiments. Finally, target area 3, you can see a photo of the experimental area as it is right now. This has already started to perform experiments. It has two focusing geometries, F40 and F20, and typically these will be used for wake field acceleration of electrons or the high energy photon beam generation from betatron X-ray generation would be typical experiments we envisage in this area. I'll come to the other parameters in a bit, but this area is interesting because it can only accept up to half a petawatt of power, but it's going to have a 5 Hertz burst mode operation available in this area, which is interesting for some high rep rate applications. So the first user experiment was actually performed in this target area 3. Professor Franklin Dollar from the University of California, Irvine, and his team were our first users. Franklin's on this tiny iPad screen over here, but he did come for the experiment, just not for the photo, and his students and postdocs are working with the ZEUS team on this first experiment. The first experiment is good for getting us to have experience as much as the users, so we know what our problem areas are, etc. And additionally, we see this target area 3 as being potentially able to expand our user base, and we want to connect with new potential ZEUS users who may not traditionally be high intensity laser plasma people. For example, there's been interest in from the material science side of things to use the electron beam or the X-ray beam for various applications, including phase contrast imaging. So we're investigating how to make a stable source of electrons and photons that might be interesting to other users. So this is probably pretty relevant to anybody who's excited to put in a proposal for ZEUS. These are the expected capabilities for each of the experimental areas. It's not quite on there, but it will very shortly be on the website, the same table. So for each of the parameters I've got over here, I've got both the 2023 and 2024, the first user year, what we're aiming to provide, what we anticipate to be able to provide in each of the target areas, and then in the brackets, the eventual capability of the area. So for target area 1, 2, and 3, you can see target areas 1 and 2 will both eventually be able to produce these 3 petawatt pulses, but the initial call will have a limited capability we need to ramp up the laser slowly, and in fact the final amplifier, we have a restricted diameter initially while our final amplifier is being manufactured. So for target area 1, we'll be able to offer, we're hoping to offer up to 1 petawatt pulses. The rep rate will be a shot per minute. Initially, for the first year, we don't anticipate offering the split beam option. For the first experiments, there's no plasma mirrors in target area 1. And so for the first experiments, we're looking at the F64 focusing. So these will be geared likely more towards Wakefield experiments, and we're not going to have the long pulse offered initially either. I'll come to the long pulse again in a moment. For target area 2, this is the one with the old Hercules target chamber that will eventually be made bigger. We're going to have to restrict the beam size, which restricts our total power we can offer. So we're looking sub 200 terawatt pulses in this area, but also offered at a shot per minute. There is no split beam option initially, and but we will have a double plasma mirror in this area, in target area 2. It'll be a short focal length parabola, and we won't have the long pulse coming in initially. And then finally, target area 3 will be eventually able to offer half a petawatt in here, but we're going to restrict it to about 200 terawatts for the first year. It'll be available in a Hertz rep rate initially, but eventually we'll be able to offer a 5 Hertz burst mode. There won't be a split beam option or plasma mirror option, but will be the longer focal lengths available for this year. So that's a kind of important table. This will be up very shortly on the website, and I'm sure there's going to be questions on this later. I mentioned a long pulse capability, and we have on order a shock driver laser. It's for Amplitude Intrepid, and it will give us the capabilities to provide a synchronized long pulse being 1.5 or 10 nanoseconds. So depending on the wavelength you want to run at, so we can run at fundamental or second harmonic, will determine what maximum energy you can get at these 2 different pulse durations. And we anticipate experiments eventually to use the short pulse capability to create probes of various kinds. So this is an example where an X-ray pulse is generated from a laser Wakefield accelerator and probes a shock driven by a long pulse in a target. And so we anticipate the long pulse being used in this way. Perhaps you have a new idea for how you would want to use it as well. Part of the experiments, we need to offer targets. So we have a target fabrication engineer, Sally Klein, who will assist with the target preparation. We have a suite of instruments for characterization that are located within the facility. I showed you the map before. The basic targets that will be available to users will be flat foils of various materials and thicknesses. We'll have gas jets or gas cells. We have experience making 3D printing different designs, and we'll be able to work with you to create your own design. So you can see example in the photo here of a 2-stage gas jet nozzle, and on the right there's a 2-stage gas cell which can have variable lengths as well. These are typically for Wakefield acceleration experiments. And we also have some experience with liquid jet targets, but we don't anticipate offering those targets in the first year. We might be able to offer you specialist targets that could be fabricated in-house using in-house machining or outside vendors to supply some of the parts, but we'll have to perform a cost analysis and assessment before we can say that we can purchase the targets, because sometimes people can invent very expensive targets and we may not have the budget for that. Diagnostics are also an essential part of the experiment. So on one hand, we're aiming to provide as many laser pulse diagnostics of what's coming through into the target area for you. The idea is that we'll record and catalogue these as part of our data management to provide the basic pulse parameters for each shot that will take place. But then for your target area, we'll have both some semi-permanent diagnostics. For example, in that target area 1 and target area 3, we have semi-permanent magnetic spectrometers to measure the electron spectra. And in addition, there'll be some sort of movable diagnostics. So we have a broad selection of these that are available. We've made a Google Sheet, which will be available to view through the website with basic parameters for each diagnostic and hopefully links to manuals and things like that. Is how we're preparing that, and that should be up on the website also this week. I have the link ready for that. We'll have information on the website, as I just said, and then the facility, you may have your own diagnostic that you want to bring and run on the facility. We'll work and coordinate with you to figure out how we can do this on a case-by-case basis. So we'll offer assistance from mechanical and electrical engineering staff to enable this where it's feasible. So we'll obviously need to have a good coordination, so please speak with us directly if you have any questions about the specifications or integration of diagnostics onto the facility. So how will the access process occur? So we're going to have an annual call for proposals. I've got more on that in a moment. We'll have an annual call for proposals for the facility. We are assembling a proposal review panel who will be independent of the facility. So no members from the ZEUS facility or QUOS are going to be sitting on the proposal review panel. We'll be granting access for fundamental research in physics, medicine and engineering, as opposed to industrial or commercial experiments. So it will be, the selection process will be done on scientific merit rather than for commercial applications, and no classified research will be conducted using ZEUS. Successful proposals that are selected by the proposal review panel will be passed to the ZEUS facility for scheduling, and will assign each experiment with a link scientist to initiate the planning process. So users are going to connect with the ZEUS user office so they can arrange their training before arrival on site, and we'll be looking to users to help us improve the facility as we go on. So we expect as part of the cycle that after, well, even during your experiment, we appreciate any immediate feedback, but afterwards we'll be looking for constructive feedback to the facility as well. So this is what the sort of experimental preparation cycle will look like. So once you've been awarded time, we'll have a series of meetings that will take place. Typically, the first planning meeting would be about 3 months out from your experiment. We'd look to identify the elements of the experimental design that require some development, perhaps from our local engineers or by the users, and we'd need to know what targets you'll be requesting at this point, so that we've got time to prepare and plan accordingly. The next meeting would take place around a month out, where we'd finalize the experimental design, review for any conflicts, design or operational problems. We'll ask people to coordinate with the user office to initiate travel plans and take all the required safety training before arrival. Around 2 weeks out, we'd have a third final planning meeting before people arrive, where we'd finalize all the experimental design and any loose ends to tie up. And then people will start to arrive, the external users will arrive for their setup weeks to actually prepare their experiment in the target area. So typically we'll be trying to offer 2 weeks of access to the area prior to your beam time starting, so that you have time to align and time, do the trigger timing, etc. in the area before you start your beam time. And the laser will not be run by the users, it will be run by the staff. So this is how we anticipate a typical experimental day going about. So we'll have 2 shifts of technicians One will arrive early in the morning to start the warm-up, alignment and maintenance of the laser systems. 8 a.m. or so, the users will arrive. We'll have a morning meeting with the link scientists and the technical staff to hear what everybody would like to do for the day. The mid-morning, we're looking to start the laser availability with first the alignment beams and then the high power beams coming into the areas. We'll switch shifts around noon each day to relieve the morning shift and move on to the afternoon shift. And then we'll have another meeting to check in and see how it's going and end the operations at around 8 p.m. each day. So really important is for users is submitting your proposals. So the first annual call for proposals for accessing the ZEUS facility is going to open this week. There's going to be an announcement to both, I'll send out to the user group email list, as you heard about the town hall for this, and the announcements will be made on the ZEUS website, and we'll advertise it any place that we can. The proposals, you've got a couple of months to prepare your proposals. We're going to ask you upload your proposal through an online submission by 5 p.m. Eastern time on 16th of January 2023. And very shortly we'll be posting the expected capabilities. That same table that I presented in the presentation right now will be available on the website very shortly. How much time will be available for this first year? We're going to be ramping up our operations. So we anticipate offering 2 experiments in each of the 3 target areas for the first cycle. Typical experiments would be of the order 4 weeks long, is what we're anticipating, but perhaps you have a more or less complicated experiment where you could justify having a longer or shorter access to the facility. You could justify in your proposal for needing a longer or shorter experiment. And eligibility, who's eligible to apply. We welcome proposals from the whole scientific community, from within the plasma community and beyond. International researchers are also welcome to submit proposals for the ZEUS facility. So please let everybody you think might be interested to be a user know that, about the proposal when it comes out, about the call for proposals when it comes out. So that brings me to the end of the presentation. I think there's some things in the chat already. So I'll just end on that we have already had our first light experiments for ZEUS, and the full commissioning is due to happen late next year when we'll launch the user operations. Please visit our website. It will be updated. A new version will be available tomorrow with the updated information, and the call for proposals will be available here as well. So with that, I am going to stop, and I'll just ask Carl, is there anything you wanted to add to the presentation?
No, I think you covered it. Yep. So I think we're just ready for any questions. There have been a few on the chat already that I've answered, but
okay, great. Okay, so I see there was already a question about the anticipated repetition rate for the electron beams driven by the different beams. So as Carl said, in target area 1 for the 3 petawatt beams, that's limited to a shot per minute. And in target area 3, initially we'll be operating at up to a hertz with the 200 terawatts, and eventually it'll be available as a 5 hertz burst mode into target area 3. Okay, next question is about the shock driving laser. Will it have any pulse shaping options? And John Nees has answered about this. So it will have, the shock driver will have an arbitrary waveform generation through an IX blue fiber front end, and I think initially we won't be offering the shock driver, is my understanding, for the first year of experiments, but we'll provide more information about the shock driver online very shortly. Okay, next question. It looks like everything's been answered already. So a question: will a user be able to deploy a rotating solid target or continuous solid foil feed target on the petawatt beam at 1 minute rep rate? For example, a continuous thin film thin target foil. We have experience with some higher rep rate targets. For example, we have the lambda cubed facility running at 500 Hertz, which requires spinning targets or liquid targets and that kind of thing. So for the initial call, I think we're starting simple, but we're definitely looking for ways that we can increase our rep rate, and other people have existing tape drives and things like this, ways to do high rep rate solid targets that we'll be looking to incorporate. Hopefully there'll be interest from users to bring their own targets of this type for us to test and install on this facility as well. And then next question is there a time frame for when the long pulse will be available? So it's going to be installed. It's just a layer of complication that's going to be added to the facility. So we anticipate this coming in to operation for the second year that we'll be offering time. All right, I think so that's the end of the questions that are in the chat so far, but I see you've got your hand up. Do you want to ask a question?
Yes, Louise, thanks. First, great talk. Thanks for the overview. So the first experimental cycle, you said, okay, so proposals are due in January. So when's the cycle start and end? 23, 24? When's the actual experimental cycle start and end date then? When would experiments be commissioned? And the petawatt experiments, you starting at 25 joule, or you expect to sort of ramp up slowly and see how it's going to go?
So we're anticipating having 2 experiments in each of the target areas for the first year. We'll look carefully at the scheduling to see so that we have prepared sufficiently for each of the areas. We have sufficient power for what's expected. So, for example, the target area 2 and target area 3 are operating at lower power. So I think it's likely in the cycle, these will be the first experiments offered, and we'll look to the scheduling the petawatt in target area 1 later in the year is the first thing. And then you asked when the cycle is going to begin. So it'll be the final quarter of 2023. The precise date for the first experiment, I think, is we'll see how that goes. And I think we are aware, first ramping up experiments can take longer, which is why we're being cautious about how many we schedule in the first year, to anticipate that we'll need to make some adjustments along the way as well.
Right. Okay, but so basically mostly 2024 for this first call of experiment. Okay, all right, great, thank you.
Okay, so there's a couple more questions in the chat. So any laser diagnostics the facility will provide to diagnose short pulse lasers? Yes, certainly. There'll be, on the facility side, we do intend to offer as well diagnosed pulse as we can. I'm sure anybody running a facility is well aware of difficulties with making on-shot measurements of every single aspect of the pulse. But we will be doing our best to make those measurements and record them, and then put them onto the database, which can then be accessed by the users. So what will those diagnostics be? Carl's put in the chat, we'll have spectrum, pulse duration, far field focal spot measurement for each laser shot. I think there are other things we can look to provide on a case-by-case basis if there's a specific need for an experiment, but those are the initial diagnostics we're targeting. So that would be from the facility side rather than the users having to take their own data of each shot. There's another question. Will there be any short pulse shaping options, e.g. Dazzler? I don't know if John is online. It looks like he is. Maybe John would be better positioned to answer this specific question.
Yeah, if you can hear me.
Yes.
Yes, we do have Dazzler as part of the system. It will be a learning process for us to come up and offer flexibility using the Dazzler. Of course, the laser chain is susceptible to damage due to an improper Dazzler setting. So it will be one of the tools available, but we'll need to use it with caution.
Okay, thanks, John. I've got another question in the chat. It's will any of the target areas have a deformable mirror available? So the short answer is yes. Now somebody can correct me, but I believe there are deformable mirrors in the laser system itself. Certainly, we have a full diameter deformable mirror available. Exactly where that's installed, I'm going to need to call to.
I can fill in there.
For it.
So we have 305 millimeter or 12-inch 3 petawatt beam line, and that has a deformable mirror. And we have a 100 millimeter beam line from our small compressor that has a deformable mirror. And then each of the beams prior to going into each of the beams in air before compression will have a deformable mirror as well. So after the beam splitter in air, there'll be a deformable mirror. So in summary, there'll be 2 deformable mirrors in each beam line, one in air and one in vacuum. Eventually, we'll have deformable mirrors associated with each target chamber, so that there'll be target area 3, a specific deformable mirror, target area 1 and 2 specific deformable mirrors. The deployment of the deformable mirrors is not fully scheduled yet, and so we can't really say that they'll be available during the first year, but we'll be working toward a goal like that.
All right. Did I miss any questions? Any more questions from the audience? And if you have more questions along the way, I will put my email address into the chat, but you can probably find it pretty easily as well. And I might not know the answer, but I'm happy to coordinate trying to answer your questions with the facility. So do contact us if you think of things. We're also preparing a special email address for the ZEUS facility that will be monitored by facility staff, scientists, and the user office as well, that we'll begin to use, but I haven't figured out how to access that yet, so please don't email that one. Okay, is there any other questions? They can be more specific questions if you wish. Or I can stay on a little longer after the recording stops, if that makes it easier to ask questions. Okay. Well, I thank everybody for turning up for this town hall. We're really excited to see what experiments come in for the facility, and yeah, we look forward to coordinating with you to get your experiments working.
Yes, and please submit proposals, and the deadline is in 2 months. So.
And the requirements for the proposals will be available very shortly. I'm doing my best to make it look similar to other proposals that you might be writing, so it's easy to translate between various facilities. Okay. With that, I think I'll ask Elizabeth, would you, oh no, I'm recording. Let me stop the recording and then maybe people